All right. How you doing? So obviously you can't answer that, but I'm just assuming that you're all doing freaking awesome. And in this video, we're taking a look at super resolution GAN, SRGAN to be specific, and we're gonna do a paper walkthrough in this video just to understand, what it's all about, how it works, the architecture, all of that juicy stuff. And then in the next video, we'll implement it from scratch. And I've also seen people mention ESRGAN, which is sort of an enhanced SRGAN, follow-up paper, I guess, on this one. And we'll probably take a look at that one next. But yeah, so let's see. Yeah, all right. So by the way, check this out. Check out this awesome animation I've been working on. Whoa, you see that? Channel's getting upgraded, man. All right. So anyways, let's get serious. So the paper is photorealistic single image super resolution using a generative adversarial network. So, we're going to skip the intro because you know what it's about. We have a low resolution image and we want to make it into a high resolution image. Specifically, they upscale it by a factor of 4 or 2, and they also experiment with 8 and larger, but 4 seems to be sort of a good ratio. Yeah. So one thing I want to mention is that what they used previously is that they used some ComNet, and then they just did a mean squared error of the pixel difference. But what they sort of the issue there is, and why we need to use GANs, is because they mentioned that here that the ability of MSE to capture perceptually relevant differences, such as high texture detail, is very limited, as they are defined based on pixel-wise image differences. So basically, that using MSE leads to very blurry looking images, and essentially it's just not a good loss function, and that leads us to using GANs. So yeah, and that is also, I guess, similar to Pix2Pix perhaps, that tried to use sort of a MSE and found the same result, that MSE is not enough, and we have to use GANs. So what they did, and here's a figure, we see the bicubic in low scale resolution right here. I think that's the low, that's the low resolution. And then or what they did in the paper is that they trained something called an SRGAN. So they trained it using only MSE, and this is what it looks like. And then they introduced GANs, and they did some other details and stuff as well, and we'll take a look at the exact stuff that they did. But essentially here it's only MSE, and here it's sort of, let's just say GANs. We'll see the details later on. But so if you just look at them, obviously this is a substantial improvement. It looks a lot better. There's so many more details that are captured compared to just the MSE. Strangely enough, the metric that they have, or the metric that we have, which is this PSNR, not really sure what it stands for right now, but that is actually higher for the MSE one than for the SRGAN one. And so we don't really have perfect metrics to measure if an image is good or not. So that is just one thing to keep in mind. And you kind of have to just look at it and, I guess, take the one that you prefer. And, probably that's the SRGAN one. All right, let's move along because we just want to focus on the important stuff, right? So yeah, right. So loss function, pixel-wise loss, such as MSE's struggle, which are typically overly smooth, and we just talked about that. So let's look at sort of the reason why they explain that is a bad loss function is that, if we look at a low resolution image, or sort of a very small part of a low resolution image, then it's possible to come from many different solutions. There are many different textures that could be correct for this specific crop. And so the MSE encourages us to take an average of all of these possible solutions, and that is what causes this blurriness. And if we instead do GANs, then we're going to take one solution. It might not be the perfect one, but we're at least going to sort of hallucinate one that could be real, which is, in general, going to do pretty well. So that is sort of the intuition behind that stuff. And yeah, all right. So what they did is that they, first of all, they set a new state of the art as measured by PSNR, which, is not a good metric because it's just for the MSE loss. So just take that with a grain of salt that they set state of the art. It doesn't really matter. But they used a 16 blocks deep ResNet optimized for MSE. And we'll see the architecture very soon. But then they also propose SRGAN, which is a GAN-based network optimized for a new perceptual loss. So what they do is that they replace the MSC-based content loss with a loss calculated on the feature maps of the VGG network, which are more invariant to changes in pixel space. So obviously, first, they introduce GANs, all right? So they add the GAN loss function. But what they also do is that they replace the MSE loss, which we talked about was a bad loss function. They replace this loss function with so they run the image through VGG 19, just a VGG network, and they compute the features that the VGG comes up with from this image. And then what they do is that they want the feature representation of the image to be the same as the high resolution image that we send into VGG as well. So what you can think about it is that just having a pixel feature, sort of a pixel representation, is not a good loss function. But if we instead bring it into some feature space through VGG, then it's going to be introducing sort of a perceptual loss instead of making it overly smooth. But yeah, that's sort of one detail that they do. And then the GAN is very important as well. So, all right. So here is, I guess, what is important, right? So here's the architecture, and what is pretty common in deep learning is that you can sort of skip everything for these types of papers and just look at the architecture, and then in many cases you'll understand everything that they did. But so, up here we have the generator, which is what produces these high quality images with an upscale factor of 4, for example. So first of all, let's start from the left. We input a low resolution image. In this case, we send it through a conv layer with kernel size 9, 64 filters, and a stride of 1. And then the padding is kind of inferred, but for all of these, it's going to be same padding. So conv, and then they use a parametric ReLU, which is, don't bother too much about it, but it's basically that instead of having it's sort of similar to leaker ReLU, except that we can decide the slope, and it's going to be different. We can basically have a slope that is different for each channel output. So, for each of these 64 channels, it could have one specific slope for the ReLU function. So, yeah, you can look more about it, but it's not too important. I think you can just honestly replace this with normal ReLU, and it's going to work as good. But so what they do is that's the introduction, or the sort of the initial part. And then what they do is that they introduce these residual blocks. So they do conv, batch norm, parametric ReLU, again conv, batch norm, and then they do an element-wise sum, basically with skip connections. So they take what they send in here, they do a skip connection, and they element-wise sum it over here, right? So that is one residual block. And what they do is that they do this right here for B residual blocks, where we have the residual connection right here, then we have one right there. So for each residual block, we sort of take the input, and after one residual block, we then add a skip connection, and we do that for all of them. And specifically, they'll mention later on, I think, that they set B to 16. So they have 16 of those residual blocks. For all of them, they only do a kernel size of 3, 64 channels, and stride of 1, which is kind of surprising to me, because so all they do is that they work with a low resolution image for some really, really long time. And that is interesting because you could imagine that they would upsample the image and then work with the upsampled image instead of working with the low resolution image and then upsample it or upscale it. Yeah. Other thing is that they do the sort of another skip connection from the beginning and then to sort of after all of those residual blocks. I guess just to make sure that there's no information that has been lost, something like that. There's no sort of cost of adding these skip connections, right? So then they do another conv, batch norm, and then element-wise sum right there. And now we get to the actual upsampling part. So for the actual upsampling part, what they do is that they take a conv layer and they output it. So from this conv layer, they output with 256 channels. And then they use pixel shuffle. And if you're not aware of pixel shuffle, basically it's going to take, it's going to take the number of channels and it's going to sort of shuffle them to the height and the width of the image. So let's say we have some channels. Let's say we have some channels by 4, and then we have, times height times width. Then we can sort of transfer that to be C times H times 2, and then times W times 2, right? So we can sort of, we can sort of shuffle these 4 times channels to be 2 times the height and then 2 times the width. And in that way, we've upscaled it by a factor of 2, right? And that is sort of, I guess, what they found to be an efficient way. I think you could also just use bilinear upsampling, but, this is how they did it in the paper. And, and so they do that for one block. That's one upsample, right? This is image times 2, and do another one times 2. So a total of 4 upscale factor. And yeah, so this is very interesting because you introduce all of these channels at the end, right? And there's sort of not much potential for the ComNet to work with that upscaled image, which is, counterintuitive to me. I would imagine that you would want to upscale it a little bit earlier and then work with it a little bit. But, if it works, it works, right? And so at the end, they just use a kernel size of 9 to 3 RGB and then stride of 1. And that is your upscaled image. Is there anything more to say here? I don't think so. So hopefully you understood the details of that. And really, this is, quite simple to implement. So for the discriminator network, what we do is we take a conv. This is, basically VGG-like, very similar to VGG. We have a kernel of 3, 64 channels, stride of 1. So conv, and then we use a leaky relu. And then conv batch from leaky relu, conv batch from leaky relu. And we do that for a bunch of blocks. And the only thing that we do is sometimes we use a stride of 2 to downsample the image. And then sometimes we use a stride of 1, then stride of 2, stride of 1, stride of 2, stride of 1, stride of 2. And then we use a linear layer right there, and then a leaky relu, a linear to a single node, and then sigmoid to make it between 0 or 1. Fake being 0, real being 1. And I think you can just also probably replace all of this with just 1D, CNN. That's, you can probably do that. But so that's the, quite simple architecture, and that's what they used. So the loss functions in this paper is really what's important. It's really what makes the difference, and also what can be quite tricky. So, they mention here that the definition of our perceptual loss function LSR is critical for the performance of our generator network. So what they do is that they take a combination of some LSRX, and so we'll see some examples of what X could represent, and then they add with an adversarial loss where they multiply with 10 minus 3 times the generator loss. So the idea that you can use for this is that either this X will be MSE, so you'll just take the pixel-wise difference, and it's pretty much as you would expect. You would just take the MSE, and then for the VGG, you'll also do pretty much what you would expect. But so you run it through some layers in the VGG network, and then you do that for the high quality image, and then you take the feature representation of both of those, you element-wise subtract the values, and you take the mean of those, right? So to be more specific, they define the VGG loss based on the ReLU activation layers of the pre-trained 19-layer VGG network, where phi ij is indicated to be the feature map obtained by the jth convolution after activation, but before the ith max pooling layer. So I think they mentioned later on that they use phi 5.4, I think. So, you just have to sort of print the VGG network and then sort of calculate to be after the fifth convolutional layer, and then after the ReLU activation, but before the max pooling, I guess. All right, so that's what could be represented as the LSRX. Either it's MSE or it's this VGG one. So they experiment with both, but so for the adversarial loss, they also include that, of course, and it's just going to be sort of the basic BCE loss that we've seen multiple times, right? And they also utilize the non-saturating trick, so just for better gradients, but nothing fancy, right? VGAN GP wasn't invented at this time. So yeah. All right, so they trained the network on an NVIDIA Tesla M4 GPU using a random sample of 350,000 images from the ImageNet database. So this is kind of hard to know, exactly which images they used, right? And this is going to influence performance depending on the data set that you use. So personally, I would like to have some more details here. Did they use any heuristic to choose those images? And yeah. All right, and then they obtained the low resolution images by downsampling the HR images using bicubic kernel with downsampling factor R equals 4. And then this right here, this sort of, it's really an assumption, right? That the low resolution image follows what is the same as when you would downsample the high quality image. And in fact, future papers, or sort of more recent papers, will sort of, I guess, argue that this assumption is not very good, because the low resolution examples that you'll find in the wild, so to speak, doesn't really hold up to this. So people have started using other things like blurring the image and stuff like that. But that is what they used anyways for this example, or for this paper. So what they do specifically is that for each mini batch, they crop 16 random 96 by 96 high quality images. And yeah, this is important. So note that we can apply the generated model to images of arbitrary size as it is fully convolutional. So this is extremely interesting, right? Because it's fully convolutional, even though you train it on high resolution 96 by 96, which is not high resolution by any standard, right? And then when you downsample, you're going to get 24 by 24, right? So you train the network on 24 by 24 low resolution and upscale it to 96 by 96. But since it's fully convolutional, you can still use it on 1024 pixel images, right? And then upscale it to 4K or something. So that is still going to work, which is interesting. And that's sort of the pro of being fully convolutional. All right, so and I guess also why it works is that if you imagine the kernel size of 3 is going to work on a specific part of the image, and it's just going to continue do that until it's finished the entire image, right? So it doesn't really matter. The same task, the same kernel is going to be applied no matter the size of the image. So I guess that's some intuition as to why it works. And then here they mentioned that we scale the range of the low resolution input images to 0.1 and for the HR to -1.1. And yeah, I don't know. This is sort of question mark. Like, why would you scale the low resolution to 01, but not. So why wouldn't you just scale them similarly to -1,1 is my question. But then the MSE loss was thus calculated on the images of -1 to 1, right? Because the MSE loss is on the high resolution images. And then they also mention here that VGG feature maps were also rescaled by a factor of 1 divided by 12.75 to obtain VGG losses of a scale that is comparable to the MSE loss. So this is also very confusing. And I think we will see some more of that. But essentially, they pre-trained. Yeah, so they mentioned that here. Actually, let's come back to this. So they also mentioned here that this is equivalent to multiplying equation 5 with a rescaling factor of 0.006. So you can just multiply that loss term with that constant instead. They use Atom with the momentum term beta 1 to 0.9. And they trained the SRGAN. The SRGAN is the one that only used MSE loss with 10 minus 4 and 1 million update iterations, which is a lot. Then they employed the trained MSE as initialization for the generator when training the actual GAN to avoid undesired local optima. And then they trained SRGAN with 100,000 updates of 10 minus 4 learning rate and another 100,000 at a lower of 10 minus 5. All right. So what they did, is that they trained this MSE only SRGAN, only training the generator, no GAN. And then they introduced GAN, and then they replaced the MSE loss, as we saw previously. They replaced that with a VGG 19, sort of a feature representation of the image. And then additionally, they add the GAN loss. But so my question is, why would you, if you're only training it now on VGG and the GAN loss, why do you have to introduce this multiplication of the loss term? So as we saw, basically what you're going to have as your loss is 0.006 times VGG plus 1e minus 3 times the GAN loss, right? And if you just see this makes no sense, right? You could just as well have multiplied everything by 1,000 in this case then and just remove these zeros here. And so, yeah, not really sure. That doesn't really make sense to me. And that makes you contemplate, so did they also additionally, right here, use an MSE loss? So did they do this so that you have, this with a constant of 1, and then you have the GAN, and then you have the VGG. But yeah, to all the explanations that I've understood of this paper is that they removed or replaced the MSE loss with this VGG loss instead. So then you wouldn't have it, but then the constant doesn't make sense. So it's kind of unclear. And one thing that's also unclear is that the constant term, I guess, you would want to have sort of the ratios between them, right? So maybe they want the VGG loss to be 2 times higher than the GAN loss or something like that. You want the understanding of why they chose those ratios instead of just saying, yeah, we use this ratio. That doesn't make it, it doesn't lead you to understand why they did that. And it's very hard to, if you use VGAN GP, for example, the loss function might be completely different, and then you can't do that, right? So yeah, in the implementation video, we'll see that I've struggled a lot with this because I would say the details of this is not very clear. But anyways, yeah, also, since this, the metric for measuring if the high quality images are good, wasn't good, right? They introduced this mean opinion score. So they basically, they asked raters, they asked 26 raters to assign the images on a scale. Yeah, which is, common for doing this kind of stuff. And all right. So then they tried different stuff. So they tried SRGAN with MSE and VGG22. They also tried SRGAN with MSE, VGG22, and VGG54. And they essentially came to the conclusion that SRGAN MSE is, let's see, it's that LR MSE is no good. And then they used SRGAN VG54, so with this 554, which is basically deeper in the network. That is the best one, and then they refer to this as SRGAN in the future. And then they also refer to SRResnet MSE as SRResnet. And then they also sneak this in that note when training SRResnet VG22, they added an additional total variation loss with weight 2 times 10 raised to minus 8. But that is, to my understanding, only when training SRResnet based on VGG22. So I guess for the good one, right, the one that we want, SRGAN VG54, they didn't use that. And then they also mentioned that MSE, so even combined with the adversarial loss, MSE provides solution with the highest PSNR values, but they are, however, perceptually rather smooth and less convincing than results achieved by a loss component more sensitive to visual perception. This is caused by competition between the MSE-based content loss and the adversarial loss. So yeah, the MSE wants to take an average of all potential solutions, and the GAN just wants to trick the discriminator, and so it wants to produce one sample that could be realistic. And in that way, they sort of compete for I guess, resources. Yeah, and then one thing here also that's very important, right, is that they could not determine a significantly best loss function for SRResnet or as SRGAN. And so this leads to a very complicated issue where you have perhaps 3 different loss terms, MSE, VGG, and the GAN, and you have to balance them in a very good way so that you still have the texture detail, but you still get the right coloring and so on. And that is something that I feel is a little bit lacking to understand how you balance those loss terms. So that is one thing to keep in mind. Also, yeah, I think that's pretty much it, honestly. So they use, the superior perceptual performance of SRGAN using MOS testing. So basically all of the 26 raters all came to the conclusion that SRGAN is closest to the actual high quality images. And let me see if there was anything else. No. So those were sort of all the details of this paper. And yeah, this is a cool application. The network is very simple, very easy to understand, very easy to implement. But the training is kind of horrible, and there's a lot of terms that you don't really understand exactly how they correlate or should correlate. And you can play around with that for a long time, like I did, and waste a lot of time on it, which is not very nice. But anyways, it's a cool paper, and hopefully you understood the key details of it. And we'll see you in the next video, hopefully, and then we'll actually implement this stuff. All right, take care, guys.